Hello, everybody. Welcome to the 9th panel of the Pivot 2020 series. This session is Geothermal Prospecting, Thermal and Hydrothermal Exploration. I'm your host and moderator, Tim Shin from Total E&P Exploration in U.S. Gulf of Mexico in the Houston office. I do have to say that my opinions are my own and not a statement from Total. I am currently filling in for Philip Ball, also of Total. He was unable to make it today. I don't foresee any planned fire drills here at my home or any 2-year-old interruptions, hopefully not at your home either. So with that, I'd like to tell you why I'm interested in geothermal. As a father and explorationist, as I mentioned before, I want to work towards positively impacting a greener, lower carbon future for my family, your family, and those to come after us, and that is why I have a burning passion for geothermal exploration. So a little bit about the session here. It will be 75 minutes, and our session here is about imagining a future where operators continued on exploring for and producing energy as they do today, but the asset that they were after was not oil and gas, but instead heat. So this panel will explore the nuances of hydrothermal and thermal exploration, geothermal prospecting in either greenfield or brownfield exploration settings, and should we simply drill deeper to access hotter rocks, or should we find shallower blind resources? Are there geological factors that complicate the process, and are all hot rocks equal? Panelists will discuss new technologies and methodologies to facilitate these inquiries, including tech transfer options from the current oil and gas techniques. So at this point, I'm going to start to introduce our panelists, starting with Dr. Karina Abesser. If you could say a few things about yourself, Dr. Karina, for maybe 2 to 3 minutes, please go ahead and start.
Yeah, thank you for having me on the panel. It's a great pleasure to be here. My name is Karina Abesser. I lead the geothermal energy research at the British Geological Survey in the UK. We are a public sector organisation and we focus on delivering public good science and research. My personal background is in hydrogeology and numerical modelling, so I've come to geothermal very much from the environmental resource assessment and sustainability side. The geothermal research that my program engages with is quite broad, sort of looking at the range of systems from the very shallow to very deep to supercritical systems. However, a key focus of our research is on supporting the development of geothermal energy in the UK. And as part of this, I'm very interested in the regulatory and policy aspects related to geothermal energy, specifically within the UK context. What not everyone might know who's watching here today is that the UK actually has various geothermal prospects, mostly in the intermediate to low temperature range. But a few places have potential for power generation. But with current technology, the main impact that development of geothermal energy might have in the UK is on the decarbonisation of heat, specifically so for domestic use. I just thought I'd mention this here because it might provide some context, as sort of the context within which I sort of operate, and it might sort of put some perspective on the answers that I will be giving later on. Thank you very much.
All right, thank you, Karina. Now, Tim.
Hi. My name's Tim Davies. I work at Turkana, and what we do is we make an imaging system that looks through the earth and maps fracture patterns up to 1 to 200 meters away from the borehole, and we do that in 3D. So what we've been trying to do is determine the position and the density and the flow characteristics along natural fractures. We image them like from the borehole. Now we also have another technology that's coming this next year, not ready yet, that is more wellbore integrity. It takes a 100 micron resolution image in 3D through the borehole, through the casing, through the cement into the rock, and it makes a 3D picture of that, can do flow around the wellbore and give you analysis of the steel, the cement and the rock bonds, etc. as a photo, and to do full data analytics, elastic property analysis, fracture orientation out in the reservoir formation, and interestingly enough, also where, of course, lithology changes. Can't say what it is yet, but we show changes. Our interest, obviously, is where can we help by demonstrating where fractures are in a formation. Can we map them so that if you're going to be pushing fluid through, we can give you the optimal location to do it in the first place, so that you're not wasting time trying to blow holes through rock that it's just not going to be productive for you. So you know, that's what we'd like to try and do. And also in the ultra hot, are you going to be running fluids through areas that have issues with connectivity, or there's some other issues in there? We'll just map it and show it. So just make sure everything is, the wellbore's good and the reservoir's good, it's fractured properly or not. If we're not looking for fractures, just as important to know that it's pure and clean. Anyway, that's what we do, and we're entering commercial operations actually now. We've just finished all of our field trials. So that's what we do.
Great, thank you, Tim. Now, Carl, if you could introduce yourself, please.
Thank you, Tim, and hi, everyone. My name is Carl Hoyland. I'm a geologist by training. I have a PhD from Stanford University in structural geology and tectonics. I have experience from an exploration point of view, somewhat in oil and gas and minerals, but most recently have been full-time on geothermal exploration. I am a co-founder and a CEO of a technology startup called Zanskar, which is focused on leveraging big data and predictive modeling to improve exploration outcomes in geothermal. As a company, we're relatively young, about 1.5 years old now, but most of our work has been focused on shallow, blind, normal fault hosted geothermal systems, which currently represent the majority of power producing fields in the US and represents one of the largest near-term opportunities to expand geothermal capacity here and abroad. I'm excited to be a part of this panel. I personally think the challenges we face in geothermal exploration are fascinating from a research point of view. They're fun to be involved with, but they're increasingly important that we address them and overcome them to meet our clean energy goals and needs. The Department of Energy last year estimated that there's greater than 40 gigawatts of geothermal potential, conventional geothermal potential in the United States, most of which is undiscovered. And most of which is blind, which means that until we get better at discovering them, those are sitting there untapped, and that the fastest way to add this low-cost form of energy is through improved exploration. And as I'm sure we'll get into later in the discussion, just looking at the geothermal fields in the United States, we have 36 of them. Half of those were found by accident, and the other half were pretty obvious to begin with boiling mud pots, volcanoes, or fumaroles at the surface. The reality is we aren't very good at finding these systems yet. And if we don't want to just sit around waiting for accidents, we need to leverage the best of oil and gas, who are real world-class experts in exploration, and combine that with the best coming out of places like Silicon Valley. And I think we're going to see a real acceleration in our ability to discover and de-risk these within this decade. Thank you.
Great, thanks, Carl. Now, Joya, if you could introduce yourself, please.
Hi, thanks. I'm Joya Falcone. I'm ranking chair in energy engineering at the University of Glasgow in the UK, and I lead the energy and sustainability research group. I'm a petroleum engineer by background, and have been working at the interface between oil and gas, geothermal, and other renewable technologies for several years now. I'm particularly interested in unconventional designs to engineer the hydraulic and thermal connection between the subsurface and the surface. And prior to joining academia in 2006, I worked with various oil and gas operators, including field experience and field operations. I'm originally from Italy, a country which is blessed with some of the classic geothermal energy resources, but also some of the unconventional ones. I then moved to the US and I spent some time in Germany, where I got experience and exposure to enhanced geothermal systems, quite different from the classic conventional hydrothermal resources. And since 2016, I've been back in the UK, dealing with the type of resources that Corinna was already describing earlier. I currently serve on the board of directors of the International Geothermal Association, on the Bureau of the Expert Group on Resource Management of the United Nations Economic Commission for Europe, on the Directorate of the Scottish Carbon Capture and Sequestration Consortium, and I'm the chair of the academic panel of the Oil and Gas Technology Centre in Aberdeen. And all of these are activities that do bring together always a geothermal component and also relate to this decarbonisation challenge that we're dealing with. In the UK right now, the clock has been set. In Scotland, there is an ambition to reach net zero by 2045, and in the UK overall by 2050. So indeed, the clock is ticking. We need to act as quickly as possible. And in summary, I'm really honored to have been invited to this event today, and I look forward to the discussions, as I'm really eager to support this transition to a cleaner energy mix, one that takes into account the many synergies that exist between the oil and gas and the geothermal sector. Thank you.
Great, thank you, Joya. Now, Joe.
Hi, everyone. Thank you, Tim, and thank you for Team Geo for putting all of this together in Pivot 2020. My name is Joe Batir. I'm a research geologist at Southern Methodist University. A little bit about SMU and the geothermal lab here. We have specialized in data collection, thermal mapping, and thermal modeling. And the lab started in the 1970s with Dr. David Blackwell. We have collected temperature data and rock samples for thermal conductivity and radiogenic heat production pretty much all over the US. Most of my work is focused on Alaska, and then several international projects as well, including Mexico and Costa Rica. That is mostly what we have always focused on, the very early stage reconnaissance style heat flow and temperature mapping and thermal modeling. I specialize in this thermal resource mapping and thermal regime modeling. As I said, I have personally research experience and exploration experience across the entire United States. I've focused on the Illinois and Michigan basins over to California. My dissertation was focused on Alaska. And most recently, I've worked East Texas and the Snake River Plain up in Idaho. With numerical modeling, I have modeled everything from volcanism generation at the crust mantle boundary all the way up to freeze-thaw cycles in the upper 3 meters of the ground. So a very wide gambit of the subsurface. Through my experiences, I've seen that thermal resources come in many different shapes, sizes, and temperatures. And I especially enjoy finding the optimization between what the thermal resource is and what the end use and most efficient use of that resource can be. It's important to understand resource potential in both temperature and fluid flow in order to optimize and most effectively produce that resource. In this way, I am a firm believer that thorough exploration, upfront exploration, is key to the success of any geothermal project, whether it be direct use, traditional, conventional hydrothermal, or EGS. My goal with my work is to produce the most accurate understanding of the subsurface in a thermal sense with whatever available data is there in order to reduce risk and hopefully reduce the cost once we start poking holes in the ground and start building the above ground infrastructure. I'm excited to be part of this panel and to share my knowledge here today with everyone, and I look forward to discussing the future of geothermal. Thank you.
Thanks, Joe. And last but not least, Dave, if you could introduce yourself, please. And unmute.
There's always one, isn't there? Yeah, no, thanks for that. Well, my name's Dave Waters. Huge respect for everybody on this panel, and thanks to everybody for organising it as well. But I'm interested in the scale of geothermal, really. I'm interested in the templates we can use that can move it from being a lot of single projects into the realm of kind of portfolio scale strategic planning, both at national and international levels. That I guess we deploy a lot in oil and gas. And I guess that's about workflows, not just the geotechnical ones, but the commercial ones, the regulatory ones, environmental ones, social ones, all those workflows that can empower that public-private investment. I'm unashamedly a bit of a new kid on the block when it comes to geothermal, so I'm still on lots of learning curves. And I guess I'm another test case as to whether oil and gas geoscientists can make that transition to geothermal. At the moment, I'm an independent geoscience consultant. I have a 25-year history in the oil and gas sector with a variety of different employers, I should say. But I get that for all the shared aspects that oil and gas has with geothermal, there's a lot that's different, very different, and especially commercially, and I'm still learning. That said, I've been looking at low enthalpy deep geothermal, a case study in the UK since about 2016. And I've been looking at the Permo-Triassic resource, which is, again, as Corinna mentioned earlier, primarily from a heating perspective. But I've been drawing on other case studies in Northwest Europe. And I'm making no presumptions as I look at that about the economic feasibility of that now. But where there are busts, I'm interested in what they are and how big they are and where the best scope for improvement lies. And in a way, I'm actually more interested in the places where geothermal doesn't quite work yet and seeing what can be tweaked to change that. And I think, as Joseph mentioned as well, that concept of customer-driven exploration, that intrigues me. And that's less about where the optimal sites are technically and more about those best matches of market to viable resource and plucking those low-hanging fruit where they emerge. Because it seems to, maybe it's naive, but it seems to me that the customer has lots of choices for energy now. So it's not enough to be technically feasible. It's not even enough to be commercially profitable. Geothermal has to be commercially competitive relative to all the alternatives that are out there, and not just now, but in the future too. So how best to get to that place and to do so continually in an evolving market, getting those workflows sorted and ready to deploy anywhere, that's what fascinates me. And maybe geothermal won't be the best option in every place, everywhere, but facilitating it, getting it more routine consideration, that's my goal. Thank you.
Great. Thank you, Dave. So I'd like to say a few words before we get started. This week is so far focused on the business, engineering, and drilling. And as many of you in the questions already have said, this session will focus on understanding the subsurface and the role exploration plays in the prospecting for geothermal resources. So simple questions like, how can understanding the subsurface help reduce the uncertainty to irreducible risks? Over the week, we have heard terms like blind resources, as some of our panelists have already referred to in reference to hydrothermal fields, or on social media such as LinkedIn and Twitter. Discussions on the serendipity, as some of our panelists have already spoken of many of the existing geothermal resources in the USA, and then exploration failure or the conceived irreducibility of the randomness of geothermal fields combined with the cost of drilling, which generally leads many to argue that geothermal is too risky of a business and not rewarding since the margins are low. So, yet, as oil and gas companies evolve into the companies that could, you have the issue of the power purchase agreement, or PPA as often referred to, be reduced as integrated energy companies try to balance the grid instability with low carbon solutions. So in this session, I would first like to examine how technological workflows and new tools are changing the exploration success. Also, a focus of Pivot2020 is looking at the development of closed-loop conduction resources, which represent a paradigm shift in the hunt for heat in the subsurface, not just water, heat and permeability. It has been provocatively discussed that thermal resources are everywhere, as we've heard very much recently, and thus, does this truly represent a paradigm shift in geothermal exploration? Before we start, it's worth noting that this week there have been discussions of both direct use and power development. In addition, discussions have touched upon conventional geothermal, as we've discussed, EGS, which is enhanced geothermal systems, AGS, which is closed-looped advanced geothermal systems, closed-loop conduction, and open hole geothermal systems. All of these have applied to low, mid, high, and supercritical temperatures, which are greater than 350 degrees C and high pressure for the supercritical. So I think we should start off the session firstly trying to define geothermal and its history before delving into the nuances of hydrothermal versus thermal exploration. And panelists, if we could, please try to stay away from all the acronyms. We have a varied audience who are beginners or experienced people. Then also audience, I ask of you to please, as you have already started to, get your questions ready in the Q&A tab. And if you want to direct it at a certain panelist, please use their name in the question. So the format will be 20 minutes with moderator Q&A. So I'll be asking questions of the panel. And then after that, we'll do 20 minutes from the audience. And we'll allow 5 minutes for wrap-up comments at the end. So first, we're going to start from the panel. Anyone who's welcome to answer some of these questions, but geothermal prospecting and the main areas that hydrothermal and thermal can be addressed within. So starting with the history of geothermal. And I think I'll start with Corinna. What is geothermal? And traditionally, where has it been found to be economic in the past, acknowledging that there are major geographic and economic differences in the EU, USA, and the rest of the world?
Okay, thank you. So geothermal energy is any form of energy that's acquired from beneath the surface of the Earth. And this includes very shallow geothermal sources from a few meters beneath the ground through to deep systems at depths of 4 to 5 or more kilometers. There are three principal ways in which this sort of geothermal energy can be used economically, and that's power generation, direct use heat, and geothermal heat pumps. And traditionally, sort of geothermal power plants were built exclusively on the edge of tectonic plates, where you find sort of very high temperature geothermal resources available very near to the surface. As technology evolved, and specifically sort of as binary cycle power plants were developed, enhanced or engineered geothermal systems became economically viable, which enabled power generation from a much broader range of geographical settings, albeit at smaller scale than from the edge of tectonic plates. And so typical installed capacity of these EGS systems are 5 to 10 megawatts, so much smaller. But we see these operation of these systems all over the globe now, in areas where there is increased heat flow near the surface. And a good example from Europe is the Rhine-Graben, where there is various EGS schemes stretching sort of through Germany, France, and developments in Switzerland as well. And I think I could also mention here a resource that's currently being developed in the UK is the radiogenic granites, which have high heat flows near the surface, and is a play that's being developed in the southwest of England, and hopefully will be proven economically soon. The second way of utilizing geothermal is direct use heat, and I've hinted at this in my introduction. It can use thermal resources at much lower temperatures, so 50 to 100 degrees Celsius. A geological setting that's widely exploited for direct use are deep sedimentary basins, which contain hot aquifers. And this sort of play is a very important resource all across Europe. Sort of the Paris Basin draws on it in France, the Molasse Basin in Germany, providing district heating at the large scale to Paris and to Munich, respectively. It's also widely used in the Netherlands for the horticulture sector, which have been sort of transitioned from grass to geothermal quite rapidly. So that's quite an inspiring development to watch in Europe. So district heating is sort of one of the main use for geothermal there. And the third way of using geothermal is geothermal heat pump systems. It could be described as a type of direct use at the very low temperature end. the technology is mostly used for heating or cooling of buildings, and it can be used virtually everywhere, but at much smaller scales. So some exciting development in the sector is sort of looking to see if abundant mine systems can sort of provide a geothermal reservoir for these systems. And if this can be proven economical, that would enable deployment even of the very shallow geothermal at quite large scales. And so I'll leave it at that, so to get others the chance to add to.
Does anyone want to add to that? All right. Okay. So that was great. Thank you, Karina. And you spoke about all of the places that have seen geothermal exploration so far and some success, but what do any of you panelists believe has traditionally constrained or limited the geographic distribution of geothermal resources? I'll start with Joya.
Thanks, Tim. I think it's the other way around. I think that we were probably looking at the wrong places, and that originally we were all looking for the super high temperature and super duper resources and going where the tectonic plates are. And now we're going more towards actually there is heat everywhere. It's down to us to how we untap it. And we've got this full spectrum from low temperature to high temperature. Some people will call it low enthalpy, high enthalpy. Some people will call it something else. But there is a use for any type of geothermal resource, really. It's up to us to find the connection. I think it relates to what Dave was also saying earlier, how to untap this portfolio of natural resources we have in a way that it does have customers.
Dave, yes. Unmute, please.
It's hard to ignore the role in many countries that hydrocarbons has played. For example, in the UK, just that the provision of cheap gas for many heating roles just places a competition there that is difficult to compete unless you take the costs of carbon dioxide emissions into account. And that's why now appetite is changing. That is one of the exciting things I find about now, is that people are starting to realize that hydrocarbons, burning them has a cost, and that changes the paradigm a little bit for hydrocarbon. It releases for geothermal. It releases a constraint that was there in the past, but is diminishing with time.
Thank you, Dave. And Carl.
Oh, sure. Just real quickly, I think it's interesting to think about the idea of ore in mining, which is more of an economic term, that you have these resources of various grades out there, but the idea of what is actually profitable to extract sort of creates this separate classification. So when we say where is geothermal, well, you're right, it's everywhere, and it's in different degrees, at shallower, deeper levels, at different temperatures, mostly from plate tectonics. But the local differences in economic needs or demands and our technologies to access them is constantly changing that line from what is economic or what might be called ore in the geothermal space. And I think that's what's exciting here, is that we're seeing that shift in real time with deeper drilling, with better imaging, with other technologies, and as we expand to lower temperatures in the system.
Awesome, thank you. So, as you speak about engineering, I think that, one of the questions is, could all of these systems, all of the places where we're finding and hope to find, as you mentioned, with expanded technology, could this be engineered for direct use? Geothermal. Anybody, starting with Dave?
Well, it's always, I think, a trade-off. I'm still learning, but it's always a trade-off to me. It seems of volume, temperature, and permeability. And I think in closed loop systems, there's always a little bit more constraint on the volume of fluid that you're accessing. But I think, given the people around the panel that have more experience with the closed loop story, I should perhaps defer to some of them. But that would be my trade-off. Yes, it can be used, but just there's a little bit of more constraint commercially because of the volumes of hot fluids that you can get out of it. So, but I'd be interested to hear what the rest of the panel will say.
And I think, Tim, you beat your hand up before Joya did, so let's go with Tim.
All right. Yeah, we have a sort of unique thing in Alberta here where, you know, we have thousands and thousands of wells from past oil and gas activity and have great heat. We got 100 degrees at the bottom. We got over 100 degrees. We got every kind of temperature we want. So it's sort of what would we like to try and do. Our problem, and this is the constraint here, is there's no market. We're a vast empty country. So, and these wells sit literally in the middle of nowhere with no grid to access to send power, no cities to send heat to. There are a few really forward-looking projects now, as we know in Hinton. There's a company with Shell, Evo, I think, is the company that's doing the system. But there's a city there, and it's the only one around for the next few hundred kilometers. So we have to find in Alberta really economic activities that can make use of free heat at the source, I think. And that's one of the problems that we have. We see the leadership in the Netherlands, you know, with like the agro sector, and I think that's fantastic. We have a very cold winter, so I'm a really big fan of the potential of direct use in the agricultural sector in remote applications, bringing food to the north, for example, where someone pays $3 for a tomato. Can we provide a year-round growth system based on geothermal? And once again, then we would look then to places like Iceland, where also a lower population, yes, higher heat, close to the surface, etc., but some very innovative things going on. So I think here in Canada and remote places, we need to think of end use must be there for the low heat as opposed to big district, because that's not going to happen. Anyway, that's all I need to say on that.
All right, thanks. So we'll go with Joya first, and then we'll go to Joe right afterwards. So
I just wanted to follow from what Tim just said. I think it's a very important point. And the same has happened also for electricity resources, that they were completely off grid and far away from an existing grid. So the same problem applies for heat and electricity generation. But indeed, we have to start considering where new opportunities might be created. So could there be users that are currently not there? And we are going around similar discussions also in the UK. I would say in preparation for Brexit, we might need to become a little bit more independent with tomatoes growing or strawberries growing. And so we might end up looking at locations where there are even such mature oil and gas onshore sites, where at the moment no one is thinking about greenhouse, and maybe we should. Thank you.
great, thank you. And Joe?
I also wanted to say similar things. In East Texas, we have 100 degrees Celsius water in old oil and gas wells, but here we've got the opposite problem where we do have a large population that could utilize that energy, but we just don't have the temperature differential. So 100 degrees here in Texas has a completely different economic value than 100 degree water in Alberta. And I think there it is, to the non-geothermal person, it has maybe the same value, and maybe thermodynamically it has the same value, but how we end up using it is important, and because of where we are, we have to use it differently.
So to continue on that, Joe, is this where supercritical fluids come in?
Yes, in some regards, say for East Texas, if we want to generate electricity, we need to have higher temperatures, and supercritical, drilling deeper and producing higher temperature resources is something where it would be beneficial. It would almost be necessary from an economic standpoint to make it work. But on that point, you still need to look at where you are and what the general thermal regime is, because depending on where you are, that supercritical may still be too deep to be economic.
All right, thank you. So all of this makes me think, you know, who have been the historical successful players in this geothermal exploration space? I mean, given that there are so many opportunities that you've mentioned now in regards to, you know, off the grid uses such as farming, and who's historically been successful, and who do you think could take advantage of all these new technologies? All right, Tim, thank you.
I think that the new technologies, and I'm going to just back off for a second and say, let's look at the enabling technologies that have come along. We're able to drill now to 20,000 feet like hot knife through butter, at least so I believe, because of all the people that have said so. I'm telling you that I can see the borehole, I can see the flow outside the borehole, I can tell you the casing's good, the cement's great, I can get 3D pictures. I can give you a map out into the formation of where all the fractures are before you even begin the thing. That's great. You know, we can have steels that work really well. We can have Rankine cycle engines or whatever they're called whenever they're doing this now. And really, we're missing one big piece. So that looking back at history, we've picked the low fruit. We've done thermal hot springs. We've taken it. Oh, it's hot enough to put a generator in. We've done that. We've done micro thermal recovery. We've become so good at it with companies like I think it's Thermocare. They do industrial heat recovery and things like that. So we've got all of that covered. What we don't have, and where the future could really be, is in the ultra hot, ultra deep geothermal anywhere. It's just a question of what do we need, how deep does the hole go, and how much power do we need out of it there, because we can do it. That's what we're missing now. We can't go into a dry, hot rock formation at will for a competitive price for, say, a solar farm that includes solar, battery, and disposal of it. If you wrap all that up, the second we can do that, that will open up geothermal anywhere big time and give us power anywhere we want it. You know, I can put one next to the city and put a gigawatt. You know, we put down 20, 30 wells of big ones into a very hot environment, and it just becomes a system. We do one, we do two, cost keeps going down. I think that the focus of getting to being able to put geothermal any place and scientifically monitoring it with the latest of the, digital acoustic sensing systems that we see, all the fiber, everything makes going after this big prize now doable. There's shortages of skills, yes, but we are now have all the individual little pieces either in a lab and worked and going to field trials, or coming out of field trials and looking for now the application. And I think with the work together with the national labs, and I think the national labs are critical here. And this is national labs, I mean that also Europe, Asia, everywhere, need to maybe have a joint venture on super deep, super hot, supercritical systems, because it's global. And remember, it's harder everywhere else because nowhere else will allow you to frack so much, right? So we have to look at systems that don't necessarily involve fracking through the ground. But so that future's coming. We can make kits for doing low temperature. We can get farms. We can do all of these things. We can't go geothermal anywhere yet. And that's kind of I wish I could afford to do one of those global challenges, like those Bezos and Gates and those guys can $1 billion prize, you know what I mean? Or a thing that we need an X prize, geothermal anywhere. And that's what I think we need, that focus, that spaceship mentality. We are going to get there. And it's my little bit of tech and your little bit of tech. Here we are. Let's go. Let's do this. So the test sites, the labs, the companies that are provided leadership technically. Obviously, Shell keeps coming up all the time here. I don't know what's going on with Shell, but nonetheless, there are other companies that are heavily involved. So let's just go for it. Anyway, get off the thing now. Thank you.
So Dave, will you be willing to fund this X Prize?
Well, I think the one point I want to make was the question of time, because one of the things against geothermal is always the high capex cost. But I think when you think about who's successful, been successful, it's been the people that have been ready to commit to an investment on a longer term scale of thinking. When we look at Germany and we look at the Netherlands, there was a commitment by their governments to invest in this relatively early, to make a strategic investment in that, And it's only really now that they're beginning to reap the reward in that, and when economies of scale are beginning to kick in and all the villages around Munich are starting to drill wells and feed into a, it's when that strategic investment is made that it makes a difference. But to do that takes longer term thinking, because the nice thing about geothermal is once you got it down there, it trundles along for a long, long time. I mean, the hotter you get, the hot, there's a bit more maintenance, but that's the beauty of it. It's longevity. And I think one thing we can do to encourage it more is just to encourage governments to think in those terms more.
And so now, Joe, what about you? X-Prize funding, anything?
No, I don't have the money, but keep talking to Bezos. I think we'll get him to throw some at us. I wanted to comment. I agree with the time aspect. I think we do need to have a long-term picture. But getting back to the original question, I think both Tim and Dave highlighted it, is that it's finding that specific focus that you're good at. And I think Ormat is a great example where they started building their generators and they knew which systems they could generate power with, and they were doing that. And eventually they got into exploration, and now they're truly a geothermal company from early exploration all the way through building and producing power. And I think that's something that Tim pointed out, is that we have all of the technological expertise. It's just a matter of putting them all together, and it really does take collaborative work and really a policy from the government that is open and inviting to that.
Joya, you were going to say something.
Yes, actually, Joe already anticipated this. Going back to the original question, who is the most successful operator? Interestingly, the geothermal sector hasn't operated in the same way that the oil and gas sector normally has. So this figure of the classic operator that does it all from beginning to end, from exploration, production to appraisal, development, and then subsequent sale, hasn't really been the norm. And I think it's important to ask ourselves the question whether that should be the norm in the future for any type of geothermal resources. Possibly not, especially when we start going for decentralized or off-grid systems, or let's also think about these smart energy distribution networks that the world is moving into. We shouldn't be talking about geothermal as an independent vector. We should be looking at geothermal as part of multi-vector decarbonized distribution systems. And something we haven't talked about at all at the moment is the actual thermal energy potential that the geo subsurface has. And per se, just that, not the production mode, heat or electricity, but the thermal energy storage capability that the subsurface has may be key in acting as a balancer for these infrastructure distribution networks for the future. So maybe we don't have to standardize and have elephants, giant operators for all types of resources in every country. And also historically, if you look at some developments, sometimes there have been also investment or co-investment by programs such as the World Bank's MAP program, which has got some of the developing countries going, and then they attract investment from sometimes the power plant operators, and then that marriage created the entire chain from extraction to sale. So sometimes the business has gone unconventionally and maybe needs to continue going unconventionally. Is there enough room and enough money that we're talking about for having classic E&P giants? Maybe yes, maybe not. Thank you.
And I'd like to switch gears a little bit here, and Carl, I'll start with you actually, following on to Joya's question, because she mentioned the exploration risks and the things that are different between, say, oil and gas exploration and, estimating resource density or the calibration of our resources in the geothermal sense. So if you could start off that discussion about how is geothermal exploration different from oil and gas, and how do you estimate those resources, and what are their costs? And that's for Joya and Carl and Dave.
Thanks, Tim. There's a number of differences, and maybe to transition into that, it was pointed out that Ormat kind of exists as this example of a vertically integrated company within the geothermal space, which has given them a lot of advantages to lower the cost of the products they offer. But even them, as sort of one of the giants in geothermal, has a market cap of only about $3 billion. And there are oil and gas companies we've never heard of that are worth more than that, let alone the majors that are orders of magnitude higher. So we're talking about an industry that still is very small. And when you think of it in that way, how much risk can they afford to take on their books? How many exploratory wells can they drill before the odds start stacking against them and they go under? And we'll probably get to this later, but the power of insurance structures or even consortiums or government subsidies and even national mapping programs that help to de-risk some of the early work have been critical to the success of some of the existing geothermal fields out there. And this kind of feeds into the cost of capital that's available to the geothermal sector. Ormat has succeeded, and they've done an impressive job of continuing to grow and expanding. But about a decade ago, there were probably dozens, a couple dozen companies in the US alone, most of whom went bankrupt. And if you look at all those projects, and researchers like Anna Wall and others have done this, you see a pretty low rate of success, maybe 15% or so actually made it to the end. And so again, this comes down to if we're all just a bunch of small juniors leveraging some investor dollars to drill a few wells, maybe the odds are 15%, but you don't know that if you drill 10 sites, you're actually going to get that 15%. That's the large number average, and we're playing with small number statistics here. And some of the differences, so not just in the cost of capital and what we have in terms of size and scale going into exploration, but what we're looking for, because it's been so small, we actually haven't fully matured our ability to estimate a resource beforehand. The last wave in the US was overestimating most of the resources by almost 10x, in many cases saying we're going to get hundreds and they get 15 megawatts out of it. And we're getting better now because we have more and more systems that we can start to empirically constrain. But we do estimates, we look at the amount of hot water, amount of heat down there. We do volume estimates like you do in oil and gas. We estimate if you were to flow it through, how long would that last, what the decline would be. So there's lots of innovations in the modeling side to get better at it, not just empirical constraints. But I think that's the power of some of these new, more scalable technologies, like Tim and others have spoken about, ultra deep, supercritical, is if you can get to the point that you know what you're going to get, your cost of capital come down, your timeline shorten, and the economics change very significantly. But as it is right now, the industry or investors still assume that we haven't gotten any better than 10 years ago, and the costs of capital haven't really come down, even on our high-grade resources. That's a little bit of a roundabout answer, but.
No, thank you. Anyone want to jump on that? Carl, Dave, Joya. Sorry, Tim, Dave, Joya, please.
I think Corinna should go first. I've already spoken quite a bit.
Joya, yeah. Go ahead.
Okay, yes, just following from what Carl just said, just imagine how many companies are actually floating on stock exchanges, how many geothermal companies are operating on stock exchanges internationally. You can count them on the fingertips. So that's part of what Carl was saying. And this also reminded me of when there was an expectation that EGS would boom in Australia, and that triggered the development of the Australian Geothermal Code, which was the first reporting code for geothermal resources. And then subsequently, Canada also adopted it in a very similar format. So that was an expectation of a market to come. And we have seen still a persistent demand to some extent for standards, for frameworks, for protocols for reporting geothermal energy resources in the US. And REL has also developed the Geo Report tool for primarily for exploration screening of resources. And so we do have indications of a need for tools that allow you to minimize the risk and to have a pre-understanding of the size of the resource. But does it then go further? Does it then go into indeed a workflow of companies knowing exactly what's coming next and having a presence in stock exchanges? We're still not quite there. And when we talk Ormat, we're probably again neglecting in a little bit the business of the low enthalpy resources, the business of the small resources. If you put them all together, assuming they can all be untapped, which one is bigger? So what is the future?
And that also brings me to a question I'd like to ask Karina, which is, low enthalpy, low temperature resources have been mentioned as a major growth area. Do exploration workflows change to access those things, Karina?
In principle, not, because we're asking the same questions around permeability, temperature, and flow rates. So I'm assuming we're talking sort of shallow geothermal here. The advantage of that sort of field is that that we have a much better understanding of subsurface properties and how the system parameters at shallower depths than we have at deeper depths. And this is because there's just more data. We have more wells, more investigative drilling into that space, which helps us constrain our parameters that we need for estimating the resource, as Carl said, and planning sort of our systems. And so with deeper systems, at least in the UK, this is true, we don't have much data points. So we have a very limited understanding of what there is at depth. And so we cannot really constrain our initial estimates of permeability, flow rates, temperatures. But as soon as we have a first well into a target resource, then that initial risk reduces, and our estimates can be better constrained, and the more wells we have, the smaller the risks will get, until to the point where we understand the subsurface and the resource, and then I don't want to say it becomes risk-free, but it becomes quite low risk. And so I think this is sort of the model in the shallow system where you have really good data sets. So the risk is quite low of not getting your return.
Dave, and then we'll switch to audience questions, because I'm seeing a lot of really fantastic questions coming in.
Okay, it was just a quick point that it depends on the type of permeability, you're after, because if we're going for naturally fractured permeability, or if we're going for permeability that's inherent within sedimentary clastics, there's a big difference in our ability to discern those. The character of permeability in sediments is fundamentally easier to predict and understand than it is in fractures. So that's just another element that helps shallow systems be a little bit less risky, I guess. Okay.
All right. So we'll just sort of play roulette here for the last bit on this. I'm going to go with Tim over here for the last bit of this question, then we will move on.
Okay, so in the shallower resources, we see thousands of wells. We've got quantitative data throughout most of the basins of the world. That's excellent. We've got thermal maps everywhere. Almost everywhere has had 3D seismic done that's got a sedimentary basin. It's all the stuff is there. In the shallow resources, the exploration can be kind of reduced risk, is that if we're in an old vertical well, we can go in an image, we can look where the fractures are. Is there a fractured network we can communicate with to get flow? If there's not, we're not there. If there is, then how can we optimize it? Some places we can say, well, we can actively frack. Well, we can't do that, so let's find the most connective cluster of natural fractures to go through. If that's there, then we have a business. So there's technical things we can do in the shallow and the lower temperatures, which are much easier. I can go to 125 degrees with imaging and sensors and stuff like that. Easy, it's not a problem. So we can de-risk a lot of the shallower 2,000 meter, 3,000 meter work. Today we can do that. But to have a complete system, we're just not there. It's too disjointed. There's no. We need to, like we talk about with ORMAT. We need many companies like that. I think that start and could do their own thing, and could try it, because these consortium are not there. Unless we're going to make one, it's going to be up to, well, I just pointed at myself a little bit, and to others that we've heard where it's going to be cowboys, and we'll go try it and see what works. And, we'll buy a well, I'll put a tube in, see if it's hot enough. Is there fractures there? Yes, there are. Okay, let's go. Let's put a greenhouse up. Obviously not that simple, but we just have to keep going.
All right, so Elon, Jet, and Bezos, please, if you're watching this, Tim has a proposal for you. So going on to some of the audience questions here for Corinna and also Dave, since you mentioned some of this, we'll start with Corinna. Are you looking for, this is from Janine Vaney, are you looking for a seal on top of the radiogenic clay types? Any particular favorite paper, resource, or heat flow model you would like to share on radiogenic granites? And this is a question about top seal.
I have to admit it's not an area of my expertise, but I think the system in the southwest of England are deep buried radiogenic granites. I'm not entirely sure about the seal, but I think the system there is sort of drilling into a vertical fracture zone and creating a circulatory system with two wells where you sort of obstruct from one and re-inject into the other. Can you repeat the second part of the question? I think I get that.
Yeah, so the second part of the question from Janine was, do you have any particular favorite papers on, or a resource of any kind on heat flow models you would like to share for radiogenic granites?
No, as I said, it's not my area of expertise, but I can, if Janine wants to get in touch with me, I can pass her on to some colleagues who do modeling of that kind within BGS.
Right. Another question then for all of the panel is, maybe each one of you could take just a short 10-15 seconds if you're interested in answering this question. As in oil and gas and mining, there are core measurements, testing programs broadly known by petrophysicists, geologists, geomechanics engineers. What would be the dream core testing program for geothermal? All right, Joya.
Everything. So what we have seen in oil and gas, we've seen a slow death of old-fashioned coring retrieval, and more reliance on well logs. Of course, there have been significant advances in that, but I'm still very much in favor of cores and then cross-correlating cores and logs. Now, for geothermal, again, we cannot generalize. It depends on where you're coring. Sometimes you're coring into completely crushed environments. For example, Corinna was referring to old abandoned mines, in which case you're basically retrieving cuttings or crushed rock, but it's not a classic core. So you need to know which type of subsurface you're getting into and plan your campaign accordingly, making sure that you maximize the value of the investment.
Okay, so right, Joe.
Yeah, just quickly, the basic things that I've measured on core are thermal conductivity, radiogenic heat production, tried to get porosity, permeability, and that's, I mean, that is what I've used for thermal modeling. And I think that those are key things that you don't see as frequently in the oil and gas sector. Porosity and permeability, yes, but not as often thermal conductivity or the heat production aspect.
Great, thank you. And for Dave, we actually have a question from Doug C. A key exploration technology in oil and gas is geophysical imaging, as we know. What are the opportunities to leverage this in geothermal? Are there any technologies that are not commonly used in oil and gas, but would be great for geothermal? For example, electromagnetic or magnetotelluric. So,
yeah, no, I think it's a good question. I think a lot of the things that are, I mean, there are better people at the table than me to talk about this, but I think a lot of the advances in land seismic are going to be helpful going forward, because a lot of things are and also just the incremental improvements in gravimag, you know, the resolution and the, you know, the gradiometry techniques that are happening, they help. I think I can see the people are lining up to add, but I just want to add that there are things that I'm quite interested in, just the ability of radar techniques to go deeper into the subsurface as well. We're seeing, things in orbit around Mars detecting, contrasts and rocks a kilometre deep under the surface there. But that requires more understanding of some characteristics of the rocks that we don't test routinely now. And I think, Joseph has mentioned some of them. Just more measurements for, thermal character of rocks, the dielectric character of rocks, understanding these things so that, when we get to a point where the geothermal industry is throwing the amount of resource at understanding the thermal character of real rocks, that it's thrown at understanding porosity and permeability, that will make a big difference.
Great, thanks. And so we'll go with Carl. We haven't heard from him in a while. All right.
Yeah, no, I really like this question. In fact, the seismology and the ability to directly image the subsurface led to an incredible revolution in oil and gas production decades ago, and it's continued to improve and resolve. There's some distinct differences from geothermal and oil and gas in what we're looking for. I mean, some simple off the top of the head ones are most oil and gas targets that you're trying to get a reflection off of, if you're doing reflection seismology, are horizontal. In geothermal, we're looking for vertical high-angle structures, normal faults and other things a lot of the time, and those don't show up very well. So you need some innovation there. The second thing is they're looking for traps and structures and strata, whereas we're looking for structures, and fractures don't image very well. They're often too small to send you a reflection back. And so when I'm looking at the oil and gas space, I see some other panelists ready to chime in here. I see two revolutions in seismology that I'm most excited about for geothermal, and any of you in the shale patch have seen this, is the increase in the number of geophones that we can deploy at the surface, right? These things have come down in cost. They're no longer connected by a bunch of strings. They don't cost a fortune to deploy, and you can deploy thousands of them over an area, high density. And at the same time, we've seen this radical advancement in our ability to process seismology data. Whether that's with machine learning algorithms that are supervised or unsupervised, or just through pure number crunching with GPUs, we're extracting more and more signal out of these data sets. And two of those are being able to look at micro earthquakes routinely. This is done for shale and horizontal drilling and fracking operations. And that's a direct constraint on permeability in the subsurface, but then also looking at other ambient noises down there using these data sets. So I think there'll be a lot of transfer from oil and gas bringing seismology tools to play on what we're looking for, which is fractures. And even if we're going to induce additional fractures or do ultra deep, we still have to understand the existing fracture network to optimally design our well field and to ensure that we've reduced the risks of induced seismicity. So I don't think this kind of exploration is going away with any of the advanced forms of geothermal that are on the horizon. We're still going to have to characterize what's down there before we do anything.
And now I'll let Tim retort, and if you could bring in some a mention of traditional aquifer drive in a traditional trapping configuration, that'd be great.
Yeah, it's kind of hold the press, right? So what we've just done along those lines, we've taken a 3D seismic survey, imaged the subsurface in a particular way with this synthetic aperture imaging technique. We image it on ultra high resolution down to depth. We've then gone in with our imaging tool, which has had a distributed fiber system behind it as well. But with our imaging tool, we then shot 360 degrees around, and we're able to match images from the borehole of the entire fracture network within 150 meters of this borehole, 120 meters. But fortunately, we're able to match up against a seismic event that we could see on the seismic. So one of the fractures wasn't a fracture fault, and it went transition to the seismic. So this allows then us to take an event which covers the basin or covers tens of square miles, and we've taken it down to a few hundred meters and correlated to it. So now we can make predictions about what else we can see in that. We can add value to that seismic by putting more resolution locally around the wellbore. And that's happened. We've seen and mapped the natural fracture patterns. We've done a stress gradient analysis. We see it. There they are. There's an intersection of them. This is where one will open. You can, with the stress, I don't know the audience, but some fractures when the pressure is put against them, they open and flow. Others, when the pressure is put against them, they close and shift it somewhere else. So you can figure out the flow patterns. And what we did was, in collaboration with the Alberta governments and the Saskatchewan governments, we were able to then put it into a flow map and add information for the models, saying this is a reality around this. How does that affect your model? And the predictive value of the model goes up. The predictive value of the seismic goes up. The more sensors, the better data we put from down the hole, the more it carries on to the other technologies. So I think some technologies may have maxed out, but then somebody else does something and it allows you to take it further. You know, the seismic, it's got a limited frequency content, a couple hundred hertz or whatever. But then we add in something that you couldn't see unless you had 500 hertz, but we put it in. Now it makes it more interpretable. It didn't have 500 hertz in the seismic, but now we've made it there virtually by addition of knowledge from another sensor. I just say the sensor integration is going to be key. The technology down the hole, it's the cement, it's the steel, it's the DAS fiber, it's the GPU that can work at 200 degrees C, etc., etc. These are all there. And they can all add to each other. And I think that we've just shown that, wow, there's something on the seismic that we're seeing here. It was fantastic, you know, but so let's just keep going. Yeah, stop now.
So I'd kind of like to continue on in this theme of what is conventional oil and gas exploration versus geothermal. Carl, you mentioned that, you know, in oil and gas, we're typically looking for, let's say, a four-way dip anticline with, reservoir drive and aquifer pressures that drive oil and gas to the surface using the water. Why wouldn't that work in a geothermal sense using some of these advanced or enhanced geothermal systems or supercritical fluids? If anyone, including Carl, wants to answer that, raise your hand, please.
So again, we do have different types of geothermal plays or resources out there. And in some instances or in some types, those methods might transfer more quickly. But there's some differences. For example, if you're looking for a fractured reservoir geothermal system that might have some cap or seal over it, storing a lot of water that can be extracted, you're still not going to see many reflectors in there. And so coming in with your 3D seismic, you're just looking at a pile of volcanic rock that's been fractured without any significant density contrast that you're going to pick up. And so you're going to see a lot of noise. In fact, a lot of geothermal fields have been imaged with 3D seismic and yielded very little results for it. In other settings, like a fault-hosted system in Nevada or Turkey, you can at least image these normal faults pretty well, but you're still not seeing the variability and permeability along that fault because we're trying to find a pretty narrow upwelling where the fluids are most coming along. And if you look at a lot of these fields, a lot of the wells are kind of centralized in a very small zone and re-injected elsewhere. But there are numerous instances where drilling even tens of meters away, you get no permeability on the same structure. And so that's why I was referring to this idea. The ability to image permeability has long been the holy grail for geothermal. And that hasn't been as important in oil and gas because you don't need the flow rates that we need. We need thousands of gallons per minute per well. And that's just not something oil and gas is ever really worried about, not to mention our long-term payback period, whereas you often get your payback within years. And so I think the challenge there is a little bit different.
That's great. You touched on a lot of things that I'm sure Nick Cameron at BP is very interested in. He mentions, for the panel, everyone, conventional hydrothermal systems require both heat and permeability, as you mentioned, Carl. What do the panel see as key uncertainties in the exploration for each? Too much heat frequently destroys porosity and permeability. So what factors allow us to find both in the same reservoir? And try to go with someone different here besides Carl and Tim if anybody's interested in answering this. Sorry, Dave.
Well, I think, there have been discussions about the closed loop conduction kind of element coming in, and I'm no expert in that, but I'll just kind of make the point that, this is an area where permeability risk is removed because your permeability is controlled by the wellbore. So that is, one instance where you can physically remove that permeability risk. I'm just, I mean, I've been working in fractured basement from a hydrocarbon perspective as well, and I'm just amazed at the technologies that do exist out there to do that when you really want to. There are a lot of seismic companies that are making advances there, and I think our understanding of the geology of fractures is increasing all the time. So I think there is still a lot of hope there.
And then Joe, we haven't heard from you in a while, and maybe Joya.
So when it comes to finding both heat and permeability, mapping the thermal regime is important. Often, as we've talked about before, if you're in a conventional hydrothermal system, there may be some type of hot spring or hot mud pot at the surface, so the system's there. And one thing that I've found interesting, various systems that I've looked at, a lot of them teeter on the strike slip to normal fault stress regime, which means they are a stress regime that is opening up. They're not in a compressive stress regime, and it just, even if you're in a compressive zone regionally, you end up finding that one area that is opening and is in extension. So I think that's an important thing that isn't, maybe I don't fully understand it and how exactly and why exactly that works, but the key to having a productive system is to be having opening of fractures and almost continual opening, where it's almost naturally being stimulated consistently over time.
Joya, did you want to say something? And then we'll go to Carl, and then we'll have some wrap up right afterwards.
Thanks. Yes, I'll be brief because I'm not an explorationist. I'm an engineer, so I'm not completely on the exploration aspect of it. But normally we tend to define a risk based on the permeability, temperature, and the chemistry. By the way, I think that should also be mentioned because it is in some ways related to the temperature you find the resource at least for the temperature, for the resources where you are tapping into existing saturation, significant saturation. But as Joe said, important is the relationship between K and T, permeability and temperature, for when you actually start abstracting fluids and or heat, because that can trigger very significant geomechanics and can therefore affect the long-term longevity of your resource, whether it is closed loop or open loop. So important is to understand what is the optimum. I think Nick's question was referring to what is also the optimum, apart from how you find them and how you target the right balance. But let's think also production mode. That's very, very important. And there is no magic formula because this KT relationship varies with the type of geothermal play that one taps into. Thank you.
All right, Carl.
Just wanted to agree with Joya there, the importance of geochemistry to this. One of the common challenges of geothermal is scaling of your wells, of the permeable pathways that you're utilizing. And the more out of equilibrium the rocks or the pipes or the system that you're flowing these hot waters through, the more likely you're going to suffer from these. And this is going to increasingly be a challenge as we move into the viability of things like EGS, fracking, where you might be bringing hot water into an area that wasn't previously hot. Because these aren't just clean water that we put in from the surface. A lot of times these waters are full of minerals. They're silica rich. They're sometimes even economic minerals, right? We haven't gotten into exploring for geothermal full of lithium or other metals that could be mined for their economic value. But the silica and calcium carbonate in these fluids are going to precipitate out if you're cooling them or heating them, and you're trying to maintain this balance to prevent that scaling. So I think that's important in addition to the heat aspect.
Great, thank you, Carl. So I think this has been particularly fun for me. We've had a lot of great discussions so far over the history, the economics, the differences between oil and gas with geothermal. We didn't get to touch up on a number of things that I had taken notes on here, such as more discussions on the technology, legal and policy, and what are the future aspects of those things. So I'd like to take the last 5 minutes here, or 6 minutes, since there are 6 of you. Let's go. Each one have 1 minute here to talk about these aspects of including legal and policy and future and any technology questions that you'd like to finalize in the last few minutes here. So I'd like to start with Corinna.
Right, thank you. So one aspect I've been sort of interested in is, and we didn't get to talk about it, is sort of who owns the heat. So I have a concern that it's in many countries it's not recognized as a resource. It's not even defined as anything. It's not a legal entity. And so how going forward, if we are to use the system at the scale that we're discussing here, how are we going to manage it? Who's going to own it? And how are we going to, address conflict? So that's one question I think we need to start thinking about now, before these systems become so popular and we haven't really thought of it. I think it's a good time to start discussing this now.
Great, thank you. Now, Joe.
Yeah, so the thing that I'll touch on the technology aspect, and something that I'm interested in, if we're looking at geothermal anywhere, I think the important part is figuring out how to map temperatures at depth where we don't have drill holes, because traditionally that's how we've mapped temperature, is measuring the temperature at depth. And some things that I've noticed and I think are areas of where we can improve this and have better ideas are gravity, magnetics, improving those and really chasing those felsic granitic bodies, and figuring out Curry point temperature, depth mapping, and looking at mantle temperatures to then back calculate deep heat flows. I think those are areas where we can make major improvements and start looking at the thermal regime anywhere, even in areas where we don't have direct measurements. Thank you.
Great. And now, Tim, if you could give us your last few words.
Hi. I think that my personal view is I'd like to see, geothermal anywhere. We just don't care. It's hot, it's deep, we can do it. But reality is that the exploration is not there yet. We can't tell exactly where the heat is down below. And so the seismic processing has to get better. It has to find a way to map the heat. Our imaging sensors, of course, they have to get better. They have to get high temperature. They got to go 200, not 150, not 120. So the electronics is a concern. The sensors, I'm only concerned with sensing things, and that'll be great. But if we can't sense where the heat is, there might be time to review the old sort of slim hole drilling, where you get a really cheap rig to go as deep as you can, fast as you can, so you can take a cheap little mining core and boom, you're out. I don't know whether there's a place for that in geothermal. It used to work fairly well, but we'll see. But I just hope that we can all find the appropriate technology, join with others if you don't have it, and let's optimize these deep wells, let's optimize these shallow wells, let's find the solutions as a group, I think is best, because oil was fragmented, but it's been here for 100 years and everyone collaborates to some extent. Everybody's worked at every company, everybody knows each other. Geothermal's not that way, and I think some of that could be good. And I think collaboration and consortiums are the way forward.
Now, Carl.
Right, kind of following up on what Joe mentioned, as we move towards searching a geothermal industry where a lot of our exploration is focused on finding heat at greater depth than we've traditionally drilled, especially outside of urban areas or outside of oil and gas fields, the new approaches to being able to approximate what temperatures are. He mentioned Curry point depth mapping, things like mapping the moho depth or the contrast between the crust and the mantle, being able to look at the brittle ductile transition zone in 3D, which some researchers have started doing with high density micro earthquake mapping, where you start to see the bottom of where earthquakes reach. All of these are proxies for different temperatures because we know the depth at which brittle failure occurs. And if we know the depth and the temperature of the moho, then we have this gradient at depth. And being able to do that across wide regions is actually really expensive, and I'm not sure any one company can do those, right? It took the EarthScope initiative a lot of money to do this across the United States. And so I think it is actually very important, if we see this as a real viable future to drill that deep, to have national support on mapping initiatives at that scale to constrain some of these fundamental science questions as to the thickness of the crust, its temperature at depth. That would be my thought.
Thank you, great statement. And not last but not least, Joya.
Thanks, Tim.
I'm sorry.
I would like to just
skip Dave, so we'll end with Dave, but I meant to go to Dave next, but we'll go with Joya next.
Thank you. I just wanted to leave by highlighting the importance that every given resource can actually be developed in numerous different ways, and it is that combination between subsurface and engineering solution that ultimately dictates the long-term sustainability or not of that site. And we've been talking about engineered system today very much only with reference to, let's say, fracking, for example, creating these artificial heat exchanger in the subsurface. But what about unconventional well designs? What about smart materials, smart cements, phase-changing materials, unconventional downhole designs? That is really important, because we have sometimes imposed on ourselves, on the geothermal sector, the burden of complying with HSC rules when it comes to well completions that came from the oil and gas sector when we didn't actually need them. And it's enough to say that the geothermal sector doesn't even have standards dedicated to how to effectively do boreholes for geothermal, depending on situation A, situation B, situation D. So I skipped C for some reasons. So maybe it's about time that we also start to recognize that we have an identity as an industry, and there are plenty of lessons learned from other sectors, but let's make the situation more favorable to us, and let's continue with thinking smarter beyond what we've already done up to now. Thank you.
I'm glad you mentioned safety and regulations, and it's been a long session. We both skipped things, like I skipped Dave. So last but not least, Dave.
Thank you. That's all right. I guess I go back to my early mantra. For me, you know, the technologies that are happening, and the more you look into this, they're just so exciting. You know, seeing how clever people are being at what they can do, and the new stuff that's coming in. For me, the thing that's really exciting is just the resource that's already there, that's accessible through existing technology that I really had little idea about until I looked into this. And it's just kind of activating that story for people, the story of the SciComm, the communication story, getting all the different moving parts talking to each other. All the bits of the jigsaw are there, putting them together, and telling governments, you have this resource here, do you want to incentivize it? It's much cleaner than blah, 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 and quantifying that for them. You know, I think we can all wave our arms about it, but, you know, doing some quantitative, hard technical grunt and showing governments, here's the scale of resource, you can work this if you want to. That's what I see, and the new technologies that are coming in too, great bonus.
Thank you, Dave, and thank you to all the panelists. This is a fantastic discussion, and hopefully all of you are listening out here, including government bodies and billionaires. We've got a lot of things that the panelists would like you to take care of here. Let's get everybody together. And don't forget that tomorrow we still have our final day on Pivot 2020. So please tune in. Please make sure that you tune in for the final sessions. And also, any of your questions that were unanswered, we'll get them to the panelists. So hopefully they'll be able to answer those questions in a timely manner for you. So thank you, everybody. Thank you, panelists, for your participation. And thank you for attending Pivot 2020, and we'll sign off now.